At 03:02 UTC on February 24, 2022, inside a consumer partition of the KA-SAT satellite network serving Ukraine, hundreds of terminals begin transmitting concentrated malicious traffic. Engineers start forcing them offline. More appear. Then the network begins losing something far more important than bandwidth. Its modems start disappearing. By 04:15, terminals across Europe are dropping away in large numbers. They do not reconnect. In Central Europe, thousands of wind turbines suddenly vanish from their operators' screens. The blades keep turning. The machines still produce electricity. But from the control rooms, they have effectively gone blind. This is the story of the satellite hack that reached a European power grid. The satellite is called KA-SAT. It sits in geostationary orbit, moving with Earth so that it appears fixed above the same part of the planet. From there, it provides broadband coverage through focused beams directed at Europe and parts of the surrounding region. People use it where fiber and mobile networks are limited. Homes use it. Businesses use it. Government institutions use satellite connections too. But a satellite network is not only a spacecraft. There is the machine in orbit. There are dishes and modems on the ground, and between them sits a management system that authenticates terminals, configures services, and keeps the network operating. The satellite can remain untouched while everything beneath it collapses. That is what happens here. The affected service is a consumer-oriented section of KA-SAT. Viasat owns the satellite and related assets, while a Eutelsat subsidiary called Skylogic is still operating parts of the ground network under a transition agreement. It is a complicated arrangement. Ownership sits in one place. Daily operations sit partly in another. Thousands of terminals are spread across an entire continent. And somewhere inside that structure is a badly configured VPN appliance. According to Viasat's investigation, the attackers exploit this device and enter a trusted management segment of the network. This is not a radio jammer pointed into the sky. It is a ground-based intrusion. Once inside, the attackers move laterally until they reach systems used to manage residential modems. They now have access to the layer designed to control the network. At first, the attack looks like denial of service. Modems and customer equipment in Ukraine produce large volumes of targeted traffic. Legitimate terminals struggle to remain connected. Engineers remove malicious devices. New ones take their place. The traffic continues for hours. But this activity also creates noise. Around the same time, the number of connected modems begins falling. Slowly at first. Then, during a period of roughly 45 minutes, large groups of terminals across Europe leave the network. Tens of thousands disappear. Most do not even attempt to return. The attackers are not merely overwhelming them. They are erasing something. Using access to the trusted management environment, the intruders execute commands against many residential modems at once. Critical information stored in flash memory is overwritten. Without that data, the terminals cannot connect to KA-SAT. The satellite remains in orbit. The gateways remain standing. The dishes remain pointed at the sky. The small black boxes beneath them are now useless. Viasat later says the modems are not permanently destroyed. A factory reset can restore them. But restoring tens of thousands of remote devices is different from restoring one modem on a laboratory bench. Some belong to residential customers. Others sit inside commercial installations. Many are scattered through areas where satellite internet was chosen because ordinary connectivity was already difficult. The quickest solution is replacement. Viasat begins shipping new equipment to its distributors. Eventually, nearly 30,000 replacement modems are sent out. Technicians travel from site to site, removing devices whose internal memory has been wiped and installing clean ones. Among the affected terminals are those connecting Enercon wind turbines. Enercon is a German manufacturer whose machines operate across Central Europe. Around 5,800 of its turbines rely on satellite communications for remote monitoring and control. Together, they represent roughly 11 gigawatts of installed capacity. When the KA-SAT modems fail, the turbines do not stop. Their local controllers continue operating them automatically. They respond to wind conditions and remain connected to the electrical grid. To anyone driving past, nothing appears unusual. White blades continue rotating above fields and hills, but the link to Enercon's service centers is gone. Operators can no longer inspect their status remotely. They cannot receive the normal stream of diagnostic information. They cannot issue certain commands or reset a machine from a central control room. If a turbine encounters a fault, the company may have to send a technician to the site. One satellite terminal has turned a remote software task into a physical journey. That distinction matters. The hackers did not seize 5,800 turbines. They did not command their blades or directly interfere with electricity production. They removed the operator's ability to see and reach them through the usual channel. The turbines are not destroyed, they are isolated. Soon, security researchers discover a suspicious program that may explain how the modem memory was wiped. It is uploaded to the malware analysis platform VirusTotal from Italy on March 15th. The file is a compact Linux executable built for MIPS processors, the type commonly found inside routers and embedded devices. Researchers at Sentinel Labs name it AcidRain. Its design is blunt. AcidRain searches for storage devices, including flash memory commonly used by routers. It overwrites their contents. It deletes files. It does not steal passwords, display a ransom message, or establish a long-term spy network. It makes the device forget how to function. Sentinel Labs finds developmental similarities between AcidRain and a destructive component associated with VPN filter, an earlier operation attributed by American authorities to the Russian government. The researchers describe the connection with medium confidence. Similar code is evidence, but it is not a signature on a confession. Viasat later says the researchers' analysis of the destructive executable is consistent with the company's findings, yet parts of the operational chain remain unclear. Public reports do not reveal every server crossed, every credential used, or every command issued. The most important clue is the clock. The Cyberattack begins approximately 1 hour before Russian forces launch their full-scale invasion of Ukraine. Missiles strike. Troops cross the border. Ukrainian institutions are forced to communicate while under physical and digital attack. The British National Cybersecurity Center later assesses that Russia was almost certainly responsible. It says the primary target is believed to have been the Ukrainian military. The European Union formally attributes the operation to the Russian Federation and describes it as part of the aggression against Ukraine. From a military perspective, the logic is simple. Before moving forces, interfere with communications. Make units harder to coordinate. Slow information between commanders. Create confusion during the opening hours, when every delay matters. But KA-SAT is a commercial system. The same infrastructure serving users in Ukraine also serves homes, companies, and industrial machines elsewhere in Europe. A command aimed through a shared management system does not necessarily stop at a national border. The result is a digital strike with a physical footprint stretching far beyond the battlefield. Several thousand customers in Ukraine are affected. Tens of thousands more lose service across Europe. Public authorities, businesses, and ordinary users experience disruptions. Wind farms in Central Europe lose their remote links. It is unclear whether every consequence was intended. The attackers may have deliberately selected geographic service areas and accepted that foreign customers would be hit. They may have focused on Ukrainian communications while treating the European outage as irrelevant. Or the disruption may have spread farther than planned because the targeted terminals shared the same management partition. Either way, the design of the network makes the spillover possible. KA-SAT itself is not destroyed. Viasat says the spacecraft, its core infrastructure, and its other networks remain unaffected. Government and mobility customers managed directly by Viasat are not hit. The damage is concentrated inside one commercial partition. This limitation is good news. It is also the warning. The attack does not require control of an entire satellite. The intruders only need access to the right administrative layer. A single trusted segment gives them a way to reach thousands of machines. The management system becomes more valuable than the hardware it controls. And this pattern extends far beyond satellite internet. Remote systems are everywhere. Pipelines use them. Ships use them. Farms, factories, and power stations use them. The connection may be secondary to the machine's main function, but it determines whether operators can monitor faults, install updates, or react without traveling hundreds of miles. Convenience quietly becomes dependency. The KA-SAT network is largely stabilized within several days. Restoring the affected customers takes longer. Wind technicians replace communications equipment across more than 1,000 sites. Gradually, the turbines return to Enercon's monitoring network. The icons reappear. But the larger system that made the attack possible has not disappeared. Civilian and military traffic still share commercial infrastructure. Remote machines still depend on centralized management. Satellites connect more vehicles, energy systems, and industrial devices every year. KA-SAT recovered. The architecture kept expanding. The next attack may not stop at the dashboard. The most dangerous part of a connected system is often the part nobody thinks about. A wind turbine looks physical. Heavy steel, concrete foundations, blades built to survive storms. But its operators may depend on a small modem to understand what the machine is doing. When that connection disappears, the turbine does not need to collapse for the system to become weaker. It only needs to become harder to see. That is the quiet bargain behind remote infrastructure. Distance becomes manageable. Maintenance becomes faster. One control room can watch machines spread across an entire region. Then the same link that creates efficiency becomes a point of dependence. Not because the technology is useless, because useful technology is trusted quickly. The KA-SAT incident shows how a digital attack can move through layers that appear unrelated. A communications network, a modem, a control dashboard, a technician standing beside a turbine. No dramatic explosion is required. Sometimes the damage is the loss of awareness. For the people designing these systems, resilience cannot mean keeping the main machine alive. It also means preserving a way to understand it, reach it, and recover it when the normal channel fails. For everyone else, there is a simpler lesson. Invisible infrastructure is still infrastructure. The systems beneath daily life rarely announce themselves. We notice them when the screen goes blank, the connection fails, and a machine that is still running suddenly feels very far away.